navigation and auditory pathway. So idea here is, as I said earlier, we try to understand these pathways and then try to build or mimic those systems either with digital VLSI or analog VLSI or mixed signal design. That's the underlying skill set which we use, but the systems are brain inspired, right? So today's talk would be mainly on the digital side based on FPGA based system, which we will be talking about. One second, there is some pop-up, right? Okay, so yeah, so I will be focusing on spatial navigation and auditory pathway today, as I said. So let's go deeper into the first system. One is spatial navigation system. So the two most important neurons or the cells which helps to build the spatial navigation system in the mammals is grid cells and place cells, and it comprises of multiple brain region, including the hippocampus and entorhinal cortex. And as I said, these brain regions are equipped with numerous spatially selective cells such as grid cells, border cells, head direction cells, which is an entorhinal cortex, and then you have a place cells into the hippocampus. And this ensuing convergence of these cells in different parts of the brain enables the navigation and path integration in the brain. So let's go deeper. What is place cells, right? So place cells were first type of cells discovered by John O'Keefe in 1971 and Jonathan Dostoevsky, which they found in the hippocampus of rats. So the place cell is a kind of pyramidal neuron found in the hippocampus that becomes active when an animal enters a place field, right? Which is a specific location in the environment. So I will play this YouTube video, which is available, and then you'll get a more insight what do I mean. And they have been found in a variety of animals, for example, rodents, bats, monkeys, and humans. And they play an important role in episodic memory, actually. And they contain information about the spatial context of a memory that takes place over there. So let me just play this. So this is from this Technion Institute of Technology lab. I've put the source here, and you can see the rat is moving into this open environment, and one particular neuron which we are observing is only activated at particular location. So that's what it means. So it encodes one particular place field of an environment. That's what it means about the place cells. All right, so this different place cells respond in different parts of an arena. So this is an arena, you can think about it as a kind of arena, square arena here. And the rat is running around in the environment, and different neuron or different place cells, which we call it, is activated different when the rat is at different parts of the arena, right? So you can see this could be different neuron, this could be different neuron, this could be different neuron, and they encode different place field actually. And this has and there's the multiple different neurons which we are showing here, and this is the trajectory of a rat when it is moving randomly in an arena, and that particular neuron is activated at particular location. So this is about the place cells which is there in the hippocampus. The next is the grid cell, which is another important neuron present in the entorhinal cortex. And it is very recent discovery by Moser couple, Edward Moser and May-Britt Moser at the Center for Biology of Memory in Norway. And Alex, can you, looks like still sharing is active, or looks like it's not? Can you please confirm?
No, it is active.
It's active. Okay.
It's because only that I'm seeing your lower bar. I think Windows bar there.
Oh, Windows bar. Okay.
Yeah.
Where all these icons. That's what you mean?
Yeah.
I'm not sure how can I.
No, but it's okay. I think
it's okay.
Like we can, yeah.
Right. Sorry about that. Right. So So grid cell is a little different from the place cells. It has multiple firing fields that fires at regular intervals in a hexagonal pattern. You will see when I play this video, and when the animal navigates in an open arena. So this is the open arena. So this is an open arena where when the rat moves around, one particular neuron or one particular grid cells encode the hexagonal pattern, and you will see that. And this both the couple were awarded Nobel Prize in Physiology in 2014, together with John O'Keefe, who discovered the place cells. Let me play this video. So this is the recording at the top. Again, from the same group, the source you can see here, it's available on YouTube. And one particular neuron, once the rate is moving around, you will see that particular neuron encode the several firing field, or you can say it is encode the hexagonal pattern over there in the arena. So you can see one particular neuron, you can see multiple firing field in the arena, right? So, and if you go to the next slide, this is what it will look like. If you just see one particular neuron, it has a systematic pattern of hexagonal structure, right? That's typically you will see in grid cells, but it could be of different scales. The grid field size could be smaller or bigger based on where it located, and we will see in the next slide that structure. So this figure shows this is the hippocampus of a mouse cartoon, and this shows the spatial scales of the grid fields along the dorsoventral span of this medial entorhinal cortex, right? So here you will see the bigger grid field, and here you will see the small grid field. And it is reported as well that on an average, grid spacing increases from dorsal to ventral, which span across medial entorhinal cortex. So you can see at the dorsal, the field size is smaller, at the ventral, the field size is bigger. And this is again the position along the axis, and you can see the grid field size. So similar, and now next is how these place cells and grid cells combine together and contribute to the spatial navigation. So it is thought that the place field, which is here, which is into the hippocampus, could be generated by summation of inputs from the grid cells over a range of different spatial scales. So you can see this is the dorsoventral structure or scale, and you will see here in the medial entorhinal cortex, you have multiple scales of the grid cells, right? So here it could be bigger, and at the ventral it could be smaller. And the same hypothesis we use in our architecture to generate the place fields from the grid cells over multiple spatial scales, right? So before we jump into that, I will just cover some more interesting cells which contribute to the spatial navigation system. So this is another head direction cells, which is also found into the entorhinal cortex and discovered by James Rank in '85. And these head direction cells are again neurons that increase their firing rate above the baseline only when the animal's head is oriented to a particular location, right? So for example, this particular neuron is only activate when the head direction is at a particular angle. So here, for example, it is around 200 degree, here is around 290 degree, and so on, right? So you have multiple head direction cells which encode the direction of the animal. And there's another border cells. These cells are sensitive to the boundary of the animal's navigating environment. However, we have not used this border cell in our architecture, but for the sake of completion, I'm just explaining to our audience that there is also border cell. Whenever the animal goes to the border of an arena, that particular neuron activates. So that's how it encodes you are end of the arena. Okay, now with this background, we try to build our brain-inspired spatial navigation model and try to build it to run for real-time applications. So here, this our architecture, which is a tri-modular architecture comprising of grid cell module, and you can see there are different layers based on the dorsoventral architecture, which we have seen, which is present in MEC, or medial entorhinal cortex. And this grid cell, as I said, comprised of neurons that fired in a grid-like patterns, right? And it's a built of distinct layer with different size of the grid field, right? And then you have a place cell module comprised of neuron that fired at one or few spatial locations, right? So it's only activate at particular place field in the whole arena, not like a hexagonal grid structure. And then you have a decoding module, basically, which is kind of 2-layer simple neural network to do the regression to find out what is the actual position of an animal, right? Because so this is just we model as a black box, but here the grid cell and place cells encode enough information so that you can decode what is the position, right? So that's the whole idea here. So again, in terms of complete model of spatial navigation, which you will find in the mammals, is contributes several cells, as I shown, grid cells, place cells, and then border cells, and there are also goal cell, conjunctive cells. There are many different cells which contribute to the spatial navigation system of the mammals. But here in our architecture, we use mainly grid cells and place cells, and also we use head direction cells as an input to the grid cells here. So let's move on to the modeling of the grid cells. So grid cells here, it models in this in our architecture, it's based on the rate-based mean field continuous attractor network, and this is the equation of this particular neuron model. And this rate-based neuron in this network takes the input from two sources. One is the feed-forward velocity inputs, okay, which depends on the input, and also it encodes the head direction as well, which we are not specifically modeling in our architecture, but we are encoding that into the input directly. So we here encode only 4 direction: 0 degree, 90 degree, and 270 and 360 degree. Not 360, I would say 0, pi by 2, pi, and 3 pi by 2, basically east, north, west, and south respectively here. And this is a simple rectification kind of nonlinear function we used in the hardware, which is kind of ReLU here. And these are WIJ is, I'll let you know in the next slide what it is exactly, but it's a connectivity with the neighboring cells, and SJ is the input from the neighboring grid neurons. So this grid cell neuronal connectivity is very important to have the grid-like patterns. And so here you will see this this two, you can think about this as an arena, and this is one particular neuron we are talking about, and this is how it will be connected to its neighboring cells. If you want to have a center surround structure, or it's more like a Mexican hat structure you will see here. And but in hardware, it's very difficult to implement because you need to have the connectivity information for all the neuron like this, right? Here we are showing just for single neuron. So we did some kind of optimizations and try to do mainly ring kind of connectivity, and it works fine with that without losing much accuracy. So that's the optimizing we did, and we approximated this connectivity using ring-like structure here. So then we have the grid cell hardware module, where we have this around it comprises of 5 distinct layers, as I said, that contribute to the dorsoventral span of the medial entorhinal cortex. And each layer out of this 5 layers contributes has 900 neurons, because we are talking about 30 cross 30 arena here, of 2D arena of 30 cross 30, and with different grid field spatial scales, right? As we discussed, if you go from dorsal to ventral, you will be having distinct size of the grid field. And in hardware, we didn't implement the whole 900 into 5, which is 4,500 neurons. Instead of that, we just implemented 60 neuron, and we use the time multiplexing approach to implement on hardware rather than implementing the whole 4,500 neurons. So that's the grid cell structure. And then you have place cell module, where you take the inputs from the grid cells. So in our architecture, we use 250 neurons as a place cells, and each neuron receives one input from each grid layer, right? So we have 5 grid layers. So one particular place cells take the input from each grid layer, and it is then linearly added to generate the place cell activation. And these layers in the grid cell, right, as I said, multiple spatial scale, right, with unique grid field size and spacing also different, right? And this weight connectivity from grid cell to the place cell reflects the dorsoventral connectivity to span multiple scales of place field size. So that way we can mimic the anatomy and physiology of the entorhinal hippocampal network. So here, as I said, our model accounts for biological dorsoventral organization of the grid cell network, where the grid cell in the dorsal entorhinal cortex have smaller grid fields compared to those in the ventral entorhinal cortex, right? So we take care of this biological plausibility here as well. And this place cell module receives input from okay, this I think I've already mentioned that, and then again it's 250 place cells, we basically use it here. So this is the whole architecture, whatever I explained here, and we did some kind of optimization to avoid the multiplications and other hard to reduce the complexity in terms of computational power and the area. So we did some kind of optimization. Instead of multiple, we use a power of 2 shift operations, and we also use some random number generation here to select which grid neurons you are interested in. So based on that, basically it helps. You don't need to store the connectivity information. You just use the LFSR, and then you run that with the given seed. Automatically, it will pick up the right neuron each time. Then you have a decoding module here, which is, as I said, is 2-layer fully connected networks with 150 hidden nodes and 2 output neurons, which estimate the position of a navigating object XY location in 2D arena based on the grid cell and place cells. So basically, the grid cells and place cells are, you can think about the encoding of the information, right? And then you have a small decoding architecture if you are interested in the estimation of the location, right? Which could be, you can think about as a present in the motor cortex, right? Where this information you can use it for kind of some motor action. So this is the video. Let me just play. This is from our hardware results. This is a small video here. Oh, it's not. One second, it's not playing. All right. So here on the leftmost panel, you can see the population activity of all neurons in grid cell fabric. You can see it's changing when the rat is moving around. So this is, we mimic into the system. We didn't run actual rat, of course, but this is the whole hardware results. And this middle panel is the activity of a single cell in an arena. So one particular grid neuron we are talking about here, and you will see, so over the time it will come up as a hexagonal or triangular structure here. And this rightmost is the spikes. Whenever it is going to this particular location in the grid field pattern, that particular neuron fires, and this is the overall trajectory of an animal. All right, so this is the same thing, but in terms of images. So here, this is the output of the grid cell model. And as I said, we have 5 layers, layer 1, layer 2, and with increasing size of the grid field. And here is a smaller, then it's keep increasing when you go from layer 1 to layer 5 with distinct spatial scales. Then there's the place cells module in the arena. One particular neuron is activated only whenever you're at this particular location. So here we are showing 5 different cells, cell number 30, 92, 132, 190, and 204. And this is basically the actual trajectory, which is in the blue. And the red one is the predicted trajectory based on our network, right? And it's very close. You're not losing much information there. So that's, we tried with different trajectories. You can see different random patterns you can think about. And here is a circular trajectory as well we tried. And then we did some analysis where we said if you increase the number of layers in the grid cells and what is the error it comes in, and when you increase the number of place cells, how the error increase or decreases, right? So here in our architecture we use 250 place cells because after that it's not much increasing the MSE. And here also we use a number of layers is we use 5, but even 4 and 3 would be okay for current applications. And the next is this all those are interested in the hardware part. There are some of the utilizations area and how much the main computation is going into the memory, because we have to use the connectivity matrix among the neuron, but others are very small in terms of percentage. So, and we think that our model could be deployed on robotic platform for path integration and navigation tasks without the need for an external sensor such as GPS. Since the computation time here of our this hardware input is very low, total execution time is 32 seconds for processing 100 kilo input samples in a normal CPU. So this, if you run the same trajectory, it will take 32 seconds for processing around 100K input samples on Intel Core i7 with 8 cores. But when we do on FPGA, it takes much lower. In fact, a few milliseconds, if I'm not wrong. I need to check that again. But yeah, it's available in the paper. So I would suggest go and take a look that paper. I think I've pointed out here. No, I think, yeah, let me just see if I have cited that. So here, you can see this paper, which is published from our lab in the neural networks Elsevier journal. So you can take a look for more details here. Now the next is let me talk about another pathways, which is auditory pathways, and there are a couple of works which we published. So it's all published results which we'll be talking about in the next couple of minutes. So in basically an auditory pathway, you have the first pre-processing stage, the cochlea, right? You get this is the outer ear, the sound enters into it, and then basically the sound convert into the electrical energy through the cochlea, right? Based on the sound energy or based on this mechanical movement of this bone structure into middle ear, the different parts of the basilar membrane vibrates, and that vibration basically picked up by the inner hair cells, which is there in the cochlea, and that is communicated to the auditory cortex. So we'll go a little bit more detail here how the pathways looks like, but this is what we'll be talking about in next couple of minutes. And I'll be talking about two pathways. One is this sound localization, and another is the sound stream segregation, which is kind of simple modeling of the cocktail party problem, how we can solve that. So some facts about the cochlea. The length and width of the cochlea is 35 mm and the width is around 10 mm. A very tiny structure, always underestimated because of we are visual animals, but it's very powerful pre-processing stage for the sound in the mammals. And number of turns, it looks like a snail shape. You can see here 2 to 3 turns it has. It has around 3,500 inner hair cells, which is basically sitting on top of the basilar membrane, which vibrates based on the frequency content of your sound information. So it especially mapped the frequency. And you have around 12,000 outer hair cells, which controls the gain dynamically. And that's what you're able to hear, tiny whisper to very loud sound. And it has, I think, almost 120 dB of dynamic range of input sound. Hearing range is 20 kilohertz, around 100 million neurons in cochlear nerve, which goes into the primary auditory cortex. So AC is auditory cortex, your primary auditory cortex. And then this all we can ignore for the time being. You have around 30,000 fibers in auditory nerve. Okay, let me play this small video. I'm not sure that you can hear, but basically what it will do, it's playing a sound, and based on the sound frequency, different part of the basilar membrane vibrates. So you can, as an engineer, you can think about it is like a FFT. When the input goes in, based on the frequency component of the sound, different parts of the basilar membrane will vibrate. So if you play a single tone, it will only vibrate one particular location. You can see here These are for single tone. So this is a mixture of tones. You can see the multiple parts of the basal membrane vibrates. Yeah, I will stop here because I think it's not audible. Looks like. Okay, so there are four important parts of the cochlea. One is the basilar membrane, which is like a FFT. You can think about a cascade structure or cascade filters. When the sound goes in, based on the frequency content of the sound, different parts of the basilar membrane resonates and it vibrates, as you have seen in the image here and in the video. And on top of that, you have the inner hair cells. And whenever this vibration touch the inner hair cells, that generate the spike, right? And outer hair cells basically control the gain dynamically of your sound or of your basilar membrane. And then you have a spiral ganglion cell, which the axons of spiral ganglion cell basically converge into auditory nerves. So let me show you in the next slide. Yeah, here. So if you see here, this red cell is the outer hair cells, and this is sitting on the basilar membrane here at the bottom. And then you have this inner hair cells, which is basically when the basilar membrane vibrates, it emits this spike, and then you have spiral ganglion cell. The axons of that contribute to the auditory nerve, which goes to the primary auditory cortex. Then based on this phenomena, or based on this cochlea, we use this Cochlear model developed by Dick Leon from Google in collaboration with him and along with my previous lab. And so currently we have this running in real time on FPGA, and we some student also build silicon on chip as well, but in Andre's lab, not here. And then we have digital outer cell model and digital inner cell model, and we have the spatial temporal automatic gain control as well in this model. So you can see here, this is the block diagram of the silicon cochlea, where you have input coming in as a sound, and this is basically cascaded asymmetric resonator. So you can think about it as a band pass filter with resonating at particular frequencies. And this is configured because it's completely digital model. And then you have a digital outer hair cells model, and then you have inner hair cell model, and then you have this coupling among different nearby filters. So this is the car part, and this is the fact part, which is fast acting compression. This adds a lot of nonlinearity here and enables the high dynamic range into the cochlea. So here we have a result without fact part or without outer hair cells activated, the first one, and it nicely match with the biological results. And you can see this is around 100 filter channels which we have used in this particular figure. And in the bottom figure, this gets adaptation when you have a signal. Let's see, in this particular case, we have giving input as a 1 kilohertz tone, and it was very loud, so it reduced the gain automatically using this feedback. So that's what we wanted to show. In real time, it can damp the gain. These are some of the time domain result of the same cochlea. So here you can see this is a channel number 0, which is the highest channel, 8 kilohertz, because this, in this particular case, we have a filter range from 50 hertz to 8 kilohertz in this particular configuration. And the highest frequency is called channel 0. And you can see the gain at particular 500 hertz, you will see the gain highest, and then rest is decreasing. And at the lower channel, you won't see anything if you play the 500 hertz sinusoidal tone. And when you have a click signal, which is, and when you play the click signal, which is like a one tap, and which has frequency content across the full spectrum, and you will see this is the response, time domain response of this different band pass or band pass filters of the CARFAC model. And this is at 70 channel response at a given time. So 0 is the highest frequency, 8 kilohertz to 50 hertz, and that particular this number, which is 50th location, which corresponds to the 500 hertz, you will see the response. And same is true for the click. Okay, so now we use this cochlea, which is a pre-processing stage, to solve two problems or two pathways try to mimic. One is we try to do sound stream segregation, so which is like a cocktail party problem, which I've been mentioning. And this is basically, here you can see this is the spectrogram, frequency versus time of a complex scene with multiple objects. Here you have a flute, a hammer, and a person speech, and you can see clearly hammer is like a click kind of sound in the middle here in the green. And for the flute, you have very high harmonics here. Same, you have a for speech as well, you have a higher harmonics and different formats here. But you should note here that the flute and speech give rise to clearly distinct acoustic events that are uncorrelated in time, and that's the fundamental phenomena or fundamental what do you call rule we will use to develop the sound stream segregation model for implementation. So you need to see this uncorrelation is important, or the temporal coherence is important if for a particular object or particular I would say particular object. If they are correlated, all the frequency components and other information would come together, right? I'll explain in the next slide. So this is basically what I'm talking about, the temporal coherence model, right? So humans are very good at solving the cocktail party problem, right? And even in a party, a person can focus on a single conversation in a noisy room, and how we are able to do that, right? So behind that, the idea came from Professor Shiab Sharma's group, temporal coherence model, and we have and later we extended to for hardware implementation with him. And here so as I said, based on the same idea, here we use the neuromorphic temporal coherence model, where we use attention signal to separate target sound stream from a mixture, right? So here you will see, let's say you have two sound source, right? Source 1 and source 2, and this is the complex spectrogram. And here the main thing comes up, spectrotemporal receptive field, or STRF they call it. You can search about this STRF fields or the filters, which is both in spatial domain and the time domain filter. So you use those STRF filters, apply over this spectrogram, and you get a bunch of feature maps, right? And then based on the attention signal, you use attention signal. It could be for example, in a cocktail party problem, or in a party, it could be a lip movement, right? Which could act as an attention, so that you are able to segregate only a sound of a person which you are interested in, right? So that's the overall idea about this temporal coherence model. And then we went ahead and built this temporal coherence model on FPGA, where we use this cochlea as a pre-processing stage, which create the spectrogram, and then we have this multi-rate filter, which is similar to STRF, a spatial temporal receptive field, and then we use the attention signal to segregate a particular stream out of a mixture, and then we are able to get the target stream. So this is the overall big picture, but you can take a look at the paper, which is published already in 2016, if I'm not wrong, and which has all the details. So here, this filter or this multi-rate filter are selective to different temporal modulation rates, right? And this is very low modulation. So it is like 2 hertz, 4 hertz, 8 hertz, 16 hertz, and 32 hertz, very low. And this covers the cortical time scale, right, in the brain. This is called cortical representation, right? So the idea is basically this captures the modulation in your speech, and you would be amazed to see why this cortical scale is only up to 32 hertz, right? Because when I'm speaking, for example, when I'm talking, the modulation of my speech can't go more than 32 hertz, right? Otherwise it would be blabbering speech, you can't identify, right? And that's what you need, this modulation filters. And when you infer in your auditory cortex, this is the rate we are talking about, 2 to 32 hertz, not more than that. So that works on top of your Cochlear model. And And as I said, then we use attention signal from these feature maps, and then you extract which use as a mask information, and then you extract the target stream. So here's some of the simple example, because we have not built the whole full-blown speech segregation model, but up to some extent we model only few filters there and try to demonstrate the working system. So here, let me play. Oh, again, I think you won't be able to hear. So, okay, let me just describe here. So we have a target speech. Okay, two utterance here. One is good morning, and unwanted speech is game over, right? And when this mixture goes into the spectrogram, and then you have one particular information about one particular speaker, right? So for example, you want to segregate the good morning word from good game over. So you have that modulation of that particular target speech, and then you use as a mask in our architecture, which I just shown. And then you extract, and this is the extracted speech from this mixture. And basically you just listen in the end, good morning, game over would be completely filtered out. So that's the whole idea here. Okay, Alex, how much time do I have?
I think we are fine with that, like another 5-10 minutes should be.
5-10 minutes, okay. All right, so another important application could be sound localization, where this cochlea would be useful. I'll just describe this quickly. So we have, so this very interesting video from BBC, and I really like this video. I thought I'll play it here. This demonstrates the capability of an animals or mammals or humans, how we are good at in localization. So you can see here the power of sound localization, right? And so the next task, we try to use it and try to first understand what is the pathways in mammals. So in human, we use mainly two phenomena to perform the localization, and this is the pathways. You can see it here. We have this two cochlea. We need, of course, we need the binaural to localize. So we have, that's why the importance of 2 years comes here. And so we use mainly two phenomena, as I said, ITD, which is difference in time, interoral time difference, which is coded in the neuron, and ITD is calculated by coincidence detecting neuron in MSO, which is medial superior olive here. And then you have an ILD, which is the loudness level difference because of the head shadow, right? So we have between 2 years, we have this head comes in, and because of that, the sound, if it is coming from the right side, there would be, because of the head shadow, the amplitude will decrease on the left ear, right? So that's what we use as a cue to localize. And this ITD works pretty good if it is below 800 hertz, because the distance between the ear is around 20.21 or 22 centimeter, right? And if you calculate, you will see if your head size is, when the head size is smaller than the half wavelength of the sound waves, it works perfectly fine, and that comes around 800 hertz. So that's why ITD works pretty well if your sound or information is below 800 hertz, which is pretty common in speech and other things. So, and you will see here another interesting things. So as I said, in cochlea, the basilar membrane encodes the tonotopic structure, right? From the start of the basilar membrane. So start of the basilar membrane encodes the high frequency sound, and the lower side, it encodes the low frequency sound, right? At the end of the basilar membrane, it encodes the low frequency sound. So you can see here, this red here in cochlea is high frequency, and if you go at the end, it is low frequency, and same tonotopic structure is present till the auditory cortex. And you can see all these pathways. You have CN, you have a LSO, you have MSO. All this have a nice tonotopic structure here, right? So in this particular in the model which we built, we use mainly ITD. We didn't use the ILD because ILD requires a lot of other models, like you need to incorporate the head shadow and modeling of the pinnas which we have, which encodes the spectral cues, right? That's what you're able to hear when the sound is coming from the top or the bottom, because of the pinnas which we have at the outside. And it is a unique structure for individual person, right? So it's like a signature for each person. And that's what, if you replace that pinna with, or if you block it, you will not be able to do that localization properly. So anyway, let's move on. So based on the this architecture or this pathway, we built this sound localization using silicon cochlea, mainly from Andre's group. Ing is the main thrust behind that, Ing Zhu. And I think I listed out the paper as well here. So she built this complete sound localization system using silicon cochlea. And we need the binaural cochlea. I mean, we need 2 cochlea here. And it's the same cochlea which I described earlier on FPGA. And after that, so here we use this 70 channels instead of 100 channels. We use the 70 channels, which means the 70 cascaded filters to pre-process the binaural signals. And that travels, so this across this filter basically act as a delay line, right? All this cascade structure act as a delay line, and that's how it would be useful when you do the correlation across different channels, right? So so we have this 70 channel here, 70 channel here, and then we do this instantaneous correlogram, right? And so this B here is basically the lateral inhibition unit, which model the CN, which is cochlear nucleus, which is the difference between this the neighboring cochlear channel here as well. And then you have, as I said, this 2 car effect act as a delay line, right? And this LI output from all the channels are compared with each other in parallel using the coincidence detection to model the MSO, which is medial superior olive, and this instantaneous choreogram, which is this X here in the circle, which does the correlation between these 2 output, right? So it would be 70 cross 70 matrix here, right? But then it would be very heavy for hardware implementation. So what we did, we just do the thresholding. Based on the threshold, we just choose either it's a 1 or -1, right? And we have this onset detection here, which is basically used to detect the signal onset, so that the choreogram are only generated during the signal present, right? Or signal onset. It helps in reducing the echo and other artifacts. And then you have this average onset choreogram, and then you use very simple regression model based on CNN to estimate where the azimuth of the sound, where the sound is coming from, right? So this is the overall architecture of this. And this is onset detection. Basically, you're just so you need an onset detection so that you can reduce the interference from echoes and detect the start of the new sound. And basically, you take in a given step whether there is a significant change in the energy or not. So it's a simple function we use, and we use the log2 so that it's easy to implement on hardware. And as I said, for simple implementation, we use this correlation function. And whenever this product is more than threshold, or in this case, the threshold is 0, we just say 1 or -1. And this whole choreogram onset, which goes as a input to the CNN, is basically you are doing averaging across 90 milliseconds. We use the window here is 90 milliseconds. So these are the important operation into that, and these are the results. But I would recommend go and take a look at the paper where you can find more details. So here we use this spoken digit. We generate our own data sets and the spoken digit in Office, and we get around this decent accuracy 2.82 degree error in the azimuth angle. And there are a bunch of other similar presents in the literature. So I would stop here because anyway I'm running out of time. So Rishikesh, Aditya and Divyansh helped us to build this grid cell or the spatial navigation model, and Ing and Andres help. These are the main coming from that group about the sound localization, where our lab is also collaborated, and the sound segregation is the work which we did in the past with Shihab and Andre long time back. So these are the main collaborators and students who helped us in this 3 project which I just explained. And thank you. I'm open to questions. And if you're interested in the works, what we do, please visit our website, which is Neuronics Lab at IISc. Thank you.
Thanks, Chetan. I think we have one question.
Yeah.
So if there are more than one sounds arising simultaneously, how does the model work?
Which model?
That is not mentioned.
In localization or in segregation?
I guess like localization would be the thing.
So it's based on the onset, right? Ultimately, you're interested in where the sound is coming from. We are not interested in what is the target stream, right? So, and that's why this onset is important, so that we are not worried about echo and other interference, right? And let's see, for example, the sound is coming from the right side, and because of the onset, right, because of the onset detection, let's see it's coming from the right side, so right cochlea would detect it first, right? So this correlation between the right and left for that particular channel would be 1, another would be -1, right?
Yeah. So while the questions come up, like I have like a couple of questions.
Yeah.
So one is like, when you compare like these systems with respect to other deep learning or other things, like
Yeah.
How does it perform, like in terms of power and even accuracies and these kinds?
So here, so for example, take an example of this um, for this sound localization, for example, right? So here our system, one thing is you don't need much training, and you're already doing a lot of feature extraction, right, using Cochlea and this correlation metrics and other thing, right? So a lot of you are doing handcrafted engineering, which is probably not there in deep learning, right? Because you need to do completely from scratch and you don't understand what's going on, right? So that's always, you get one advantage in all the model which I presented. Even visual saliency is one of the good case which I didn't get time to present, but there also it outperformed. I should not say outperform, but at least in terms of power and performance, it outperformed the deep learning, because you already have a handcrafted features which you don't need to learn, and you just kind of you fix the parameter and it works pretty good. So same thing applies here. Yeah.
So does it mean that one would need to really understand the how the system works, right?
At
So,
least the bigger principle, right?
Right.
And this is again as a model, right, based on the experimental data, right?
Yeah.
So this is all we have not developed any model because we are not neuroscientists, but this is what we worked with a couple of people. For example, with Shihab, he developed this temporal coherence model, and he's well known in the community. And then we worked with him, and that's how this sound segregation came up a long time back, in fact.
So right now, the some of the implementations were shown in FPGA. Do you think it would make sense to go further into ASICs or mixed signal chips? Or
so see, right now, first we just want to demonstrate the feasibility, right? I would not recommend to go for ASIC or something unless there is any real need or there is any real application where you really want to see the power, performance, and area metrics, right? The idea is just, can you show some prototype and say, yeah, it works.
Yeah.
Because if you go for ASIC, it's always a long time to get the chip back and then testing, and it's not easy unless you have real motivation. Yeah.
Right. From an academic point, yes, but from an industry point of view.
From industry points, yes. In fact, a lot of people have been using this Cochlea model, and some of the startup has used this model because we have the Verilog code. Then they want to deploy in ASIC, because you always need, whenever you want to do sound, you need a pre-processing stage, right? And output of this Cochlea also, currently in this application which I mentioned, we are not using a spiking model, right? But SGC, which I talked about, spiral ganglion cell, you can model as a leak integrate fire model or any other kind of neuron model, and it will give the output in terms of spike.
Yeah.
So same model can be used for a spiking network as well, because you always need some kind of pre-processing.
And from an algorithmic point of view, when you look at the system, like in a deep learning system, it's much more simpler than what is proposed, right?
So but might not be lighter, right?
That is true. That is true. So for someone to get started in this field, like, does it mean that they need to start with neuroscience and then learn the algorithms, or how does it work?
So first, I would say start with the problem. What problem we want to solve, right? Because sometimes it's not always this. Because as I said, right, we hardly knows how the brain works, right?
Yeah.
So sometimes even the problem could be easily solved with simple algorithm, which is maybe brain inspired or doesn't need to be brain inspired. Even deep learning works fine for some of the cases, right? So I mean that's my approach, at least coming from engineering background. We want to solve a problem, and now which one is better? We just want to see, because a lot of time you don't have data, right? Then how would you do that? So especially in the sound localization, right, it's very simple. If you see, you just get the data, you just do the correlagram, and you just need a simple regression, right? And that works fine. But on top of that, if you want to train the neural network, you need a deep learning, you need a binaural signal maybe, and then you need to have a lot of data which would work only for that particular environment.
Yeah. So, and another question is like, how do we benchmark this?
So this we benchmark actually. Yeah, we benchmark in the paper that particular sound localization at least. And another thing I didn't explain, which is visual saliency, that we also benchmark even with other networks.
Okay, so it's basically like other algorithms. And,
yes, correct.
And is there anything that is with reference to the neuroscience? Like, is there any standards that needs to be met?
So yes. So in terms of neuroscience, so if you see in this table, in sound localization table, which I think, if you see this is basically the human result which you got.
Okay.
And same in when we did for the saliency, unfortunately, we, as I mentioned, we couldn't because of time. But there we use the eye tracking model.
Okay.
So that also worked with Ralph and his student long time back.
And that might take more time to do it, right? So
correct. Maybe some other time we'll explain. But basically, these are the pathways which we worked on, and we thought would be interesting to show people how you can connect from or brain inspired model. Can you build something useful? So that was an idea for the talk.
I think that's a very big barrier, right? Like, when it comes to deep learning, there are so many different tools and easy to use like techniques out there now. And
yes.
You don't have to worry too much about how features are formed.
Yeah.
Whereas like when you look at like something like what you proposed now, which needs a certain level of understanding about at least certain
pathways. Yes, very interdisciplinary as well, right? Very interdisciplinary into the nature. And deep learning might work, but sometimes when we see results, it's difficult to replicate most of the time, I found. You can't replicate. Might be in paper they might have shown, but difficult to replicate. And maybe they know the recipe, what are the variable you need to crank it to get this optimal results. But I'm not sure whether it is true all the time.
So in terms of practicality, like, the performance wise, is these methods performing better than deep learning, or are they falling short on something? And
I think I can't comment on exactly, because unless we build corresponding deep learning, right? Because deep learning also there is different layers, different number of layers, and then because we are here talking about the hardware, right? And then we need to build them and then see how much it comes. But at least one thing is, here we know why it is working, and then deep learning, at least I don't know why it is working most of the time. It's just black box.
That is true. You just rely on the training mode.
Yeah, here at least we can tweak. If something is not working, we know at least why it's going wrong.
There is one question. As far as hardware implementation is concerned, what about the area, power related aspects?
I mean, specific to particular application you're talking about, or?
I think.
See, whenever you implement in this parallel architecture,
application, that's what.
Yeah, so you will always get benefits when you go either in VLSI domain, either FPGA or analog or digital, because you get the parallelism, right? And that's how even in the brain all the architecture is based on, right? So you'll always get better PPA matrix as compared to running on the CPU, right? This is the general answer. But if you have any specific question for a particular model, then I mean, then you can. I mean, I'm not sure what exactly you mean.
So that needs like to. I mean, you would have to look at like the implementation itself, right? So
Correct. Yeah. And then see, for example, even we work on now edge computing, right? And we did some of the speech-based tasks, and we were able to port even this Cochlea model and other things, and we were able to get even less than 10K LUTs, right? And the power we are talking about 7 milliwatts. So we did recent work where we did this what do you call sound detection, right? Which sound it is, right? Where we use Cochlea as a pre-processing stage, and then we are able to squeeze this up to within 10K. 10K LUT is very small.
okay.
And you can do a lot of applications. So this is one of the tasks which we did recently, and it performed really well for edge computing or TinyML kind of task, right? Because you always need some kind of pre-processing for sound, right? People use MFCC, but MFCC is very hard to implement, right? Because you have a filter bank, then you have a log, and then you have a DFT, and then again log.
Hardware implementation is
right. But here's a biological processor. It works pretty nice, and it has a performed really well, and that's what we have been using. We have used in a couple of our papers. I think if they are interested, they can take a look on the website.
Right. So at the end, I mean, you do have like still like the vector multiplication going in, right?
In
one
Cochlear
of the
model.
Cochlear model.
Yeah, because it's maths in the end, right? So if they have, yeah, you need to do
so
that.
So basically, the same things that you would use to build like in deep learning, you can use some of those things there as well.
Yeah, correct. Another thing is also, if you're using in the pipeline deep learning along with the Cochlea, right? You can, in fact, replace the MAC operations with some approximation, right? As long as it has this resonating structure, the rest of the things can be taken care by the learning stage. Right, and that's the advantage of learning. If you are learning with that, you don't need that accuracy. So you can do a lot of hardware tricks or approximation there.
Okay, I think if there are no further questions, I think we'll close it for close the talk for the day, and we'll move to the next one. So thank you, Chetan, for joining in and giving your thoughts and your work, the details of your work.
Yeah.
So next speaker.
Okay. Thank you, everyone. Okay, just stop here.
So if you would want to join in for the next panel, you're free to join. So what we are having is we have like 20 minutes of a talk by Manu, who is in the industry. He has been working on SNN and other things. Right. And after that, after the 20 minutes, we'll have a panel discussion.
Sure.
So that
I would see. Yeah.
Okay. So Chitra, if you could do an introduction.
Yeah, sure. So thank you, Dr. Chetan Singh Thakur. That was an interesting session on hardware system mimicking neural path. So